cloud computing, algorithms, data science, web. These are the four elements that a master in CS should be able to know. And long ago, when I was back to being a student, it was all working in harmony. Then all of a sudden, the cloud computing clan attacked. Only the avatar, master of all four CS elements, can save the world. So yep, welcome to season 3. Happy Mother's Day or Muqingjie for those who celebrate. I actually want to dedicate especially to my mother. Once again, just doing an amazing job raising me to be a good computer science, data science guy, and just like learning to solve algorithms really appropriately. I think it runs in the family, which is great. So before I begin, this season 3 is gonna be a little bit different. So I've decided to finally bite the bullet and use WordPress. I usually don't want to use WordPress because it's a little bit cheapened for like building a website or like, I tend to like build websites from scratch, but due to time constraints and simply just, I guess, for simplicity reasons, I chose WordPress. So lo and behold, here is my WordPress website for season 3. So you see from a WordPress, it's quite decorative. Like I have basically very nice responsive design for my WordPress episode. It's also basically live, which means like it's timed based on episode release. So I just want to thank Optum UHG, Dell, Northeastern, BU, CTCI, Kraken Coding Interview, my mom and dad, CTCI again because it's very important, LeetCode, Kubernetes, CK80, and viewers like you. So for episode 1, we're going to go over something very basic and very important for computer science, bit manipulation. So before we begin with bit manipulation, we must ask what it means to manipulate a bit. Or better yet, what it means to look at a bit that does something like this, counting down to the next episode. So I'll give you guys a moment to think about it while I bring out the whiteboard. Okay, so I have a new whiteboard here. So I have a new whiteboard here, okay? So what it means to have a bit manipulation. So let's say, for example, you're at Mother's Day and you want to buy a bunch of flowers for your mom, if she requires it, right? And let's say there's a bunch of roses, and then all of a sudden there is an unwanted dandelion. Me having some pollen allergy, I don't tend to enjoy the dandelion because they like fluff away and they cause you to sneeze. So you want to basically reduce the dandelion as much as you can. So there's an algorithm for that, the min-max algorithm, which is essentially reduce the unwanted outcome much as you can. However, the min-max algorithm doesn't work in one particular case. What happens if everybody except one particular bit, or in this case, one particular flower, is something you don't want? So that's when you get into bit manipulation. Essentially, it's not only just flipping bits from 0 to 1. That's not what bit manipulation really means. It means more like essentially optimizing your code by manipulating the bits. So it's not just like, LeBron, flip the switch on and off like the NBA playoffs. It's not like that. It's more just learning how to optimize your code by manipulating bits. So as like a brief exercise, here is a question that I got from my undergrad in terms of bit manipulation. So what is basically x and zeros equal to? Well, this should be pretty simple. It should be a bunch of zeros because just like multiplication, it's almost like doing a form of computer arithmetic, like the stuff you do on your calculator. It really is just that simple. It's just like knowing that x and zeros is a bunch of zero, and x and ones, of course, is going to be a bunch of ones. So what happens if I make it a little more advanced? And instead make it not ands, but ors. X or zeros, what would happen here? Well, just like choosing the roses and dandelions, you could either have all roses or all dandelions. But since you want the optimal outcome, it's going to be x's, so a bunch of x's. Same thing holds for x or ones. There's also going to be a bunch of x's. So you can see this is sort of like relating to truth table manipulation a little bit, like being able to understand truth tables more than anything. And this is actually a very common interview question for like, I don't know, for like companies that tend to do a lot of like analog and device work and like, some circuit design and those type of things. Even like with database and the admin stuff, you want to know your bit manipulation really well. So if you want to know bit manipulation really well, I would suggest actually looking at not only the Wikipedia website, but also look at CTCI chapter 5, or in very common terms, Gail Lackman McDowell's chapter 5. This is something that like will help you understand bit manipulation, and also it's sort of a motivation for the Algos in 10 season 3 questions in general for the season. Like being able to understand what Gail is saying in these particular contexts will be very helpful in terms of understanding how to solve the problems for today. And honestly, if you're struggling with leak code or like solving interview problems or just having a really hard time trying to crack those OAs, I think this is like a good step back, like a throwback to something that's a little bit easier to understand. Because one of the main complaints from season 2 was it was too high level, it's too advanced. And I agree, data science is complicated, and to rush through that in one season, given even with the masters in that is tough. So rather make it more chill out this season, like make it more from the heart, or in the spirit of my mother, make it more from the heart, from what you truly know, not just something you just found on Wikipedia and say is your own. That's not being honest with yourself. And I'd rather just be honest about my skills. So without further ado, let's look at the problem sets we're going to solve for today. So let's look at the problem sets we're going to solve for today for the bit manipulation. So problem 1 is pretty simple. It's basically flipping bits. So if you have never watched Avatar: The Last Airbender, you can tell that this is going to be related to that. So a little bit of a spoiler alert. Let's just say hypothetically Aang is stuck in Ba Sing Se, and he actually was doing this after he defeated Fire Lord Ozai. As it happens to be Mother's Day in Avatar Nation, he wants to help his better half Katara commemorate her mother who died in the Fire Nation siege, which is sad. But Katara has a bag of flower seeds that needs to grow with water. So Ba Sing Se's Records of Nations gives Aang and Avatar 4 BitBending problems, which is a bit of an Avatar reference, water bending, fire bending, all that good stuff. So if you can solve them in time without cheating, which means without looking at the answers, the Record of Nation will give Katara exactly the amount of water required to water bend for the set of flowers to grow and give Mother Spirit. So it is up to us, Team Algos in 10, to team with Team Avatar to help Katara on this very special day. So problem 1 is pretty straightforward. You're given a set of water drive beads M to N, each with 32 beads on each bit string. We're also given the 2-bit positions J and K. So you need to devise basically a divide and conquer method to insert one set of beads M into a set of beads N, assuming you can use arithmetic right shifting for like bit manipulation, such as that M starts at bit Bj and ends at bit Bk. So as an easy example, if we have a bead that's the colors blue, white, white, blue, blue, then we can assume that at least 5 bit heads between J and K. We cannot have bit heads of length 3 for J and length 2 for K, since J is strictly less than equal to K, and M cannot fully fit between bit bead 3 and 2. So devise a divide and conquer bit shifting method or algorithm that runs in linear time. So I'll give you guys a few moments to think about this problem, then I will show you the solution on a whiteboard. And by the way, because this is something that I sort of come out of the blue, I will not actually post the coding solution till later. So hold on tight for that. So you can begin thinking about what it means to manipulate a bit. So let me quickly pull up the whiteboard again that we just used. So to manipulate a bit, you need to think about masking. So this is another term that bit manipulation commonly uses, is masking. It's not wearing the COVID mask, masking. It's more like just using an operation to change the value of the bit. So for example, a very common mask that I think a lot of people in comp sci use is 0x and then like the Fs. It's basically all ones mask. This will be very helpful to know like which bits are truly one once you manipulate them. Another very common mask is basically the hexadecimal all zeros mask, which is essentially the 2's complement of the all one mask. So, or in layman terms, it's basically like the opposite of the all one mask. Masking in itself, coding wise, gets complicated. So we're only going to use the most basic masking just to like keep things simple. So here's a very simple problem I want you guys to solve while I show you the solution for the part 1. What is X and the all zero mask equal to? So you guys could at least be able to understand the implication behind what it means by having an all ones mask. So essentially, when you have 0x and a bunch of Fs, or basically binary all bunch of ones, you're essentially just having identity function. So it's going to be equal to X again. So the answer to this solution is X. This is what we call the identity mask in computer science. So now with this masking background, we can solve problem 1. So with this, I'm going to do the following. I'm going to slightly shrink the website so it actually could like fit my whiteboard and have a split screen thing. So here we go. Here's a split screen. So we're going to delete this because that's no longer useful. And we're going to now give you the algorithm. So this is not the entire code. This is just pseudocode, like what Gail would do in her book. So essentially, you have 3 main tasks to do for this thing. The first one, obviously, is to clear the beads, essentially. So clear the beads. Actually, no, clear the beads with the bit bead j and ending at bit bead k. Because all we really want to do is basically turn everything to all blues and all whites. Okay, step 2. You want to sort of line them up a little bit. So use arithmetic right shifting to line up bits j through I. Now you're wondering, Jason, why is it j to I? Because you have to think about the positioning of the beads. So to illustrate that, I have a quick example that is basically the same example with like indices. So you have blue, white, white, blue, blue, right? So this is position I, this is position J, this is position K. Because we're arithmetic right shifting, that means we are sort of doing a division. We're sort of like making the number smaller here. So arithmetic right shifting, or this, means division. Arithmetic left shifting, and correct me if I'm wrong for this, by the way, is going to be multiplication. It's very easy to get shifting operations wrong, so do be careful with your work when you're doing shifting. But I'm pretty sure this is correct. So with arithmetic right shifting, you got to make sure you basically reduce the colors of the other bead. Okay, moving on. Step 3, very important. You got to merge. So this is a very, very loosely based divide and conquer here. As you remember from basically season 1 and part of season 2, and just in general computer science interview questions, you got a divide step right here. So you got the divide step clearly here is to divide all the problems into like shifting the beads. This is clearly the conquer step, which is basically trying to put it together. And here it's going to be the combine step, which means to basically put it all together with the runtime required. So with that being said, I'm going to tell you the solution for this problem very, very loosely. This isn't really a rehash of how to write pseudocode. It's more just understanding how I come up with my solution. So we have a very basic Java function, update beads, and we have 3 main variables, int I, int j, int k. Gale uses 4 variables. I think that's a little overkill because you don't really need the 4th variable. You just need like 3 of them. This is another beauty of bit shifting. You don't have to like actually reuse the variables all the time. So I'm going to just clear drawings again and write the algorithm. So here is the base case for this so-called, I guess, recursive algorithm. If simply the bits are no longer in order, if I is less than 0, or if j is greater than 32, because we're looking at basically the 32 beads on each bit string, which is essentially a mention of floating number. Actually, no, sorry, integer, mention of integer number. You return 0. This is the base case. Now you got to make the mask. So we're going to make a mask called, now Gale uses tilde0 in her solution. I'm going to just basically make it a bunch of zeros to make life a little easier and easier to read. And now we're going to do the following. If left, so now we're going to have a variable called left. And left has 2 choices. You could either have j less than 31, or this is a ternary operator, or you can have the shifting already happen. Mask shift j plus 1 is going to equal to 0. So this is what I call a ternary operator in Java. Next, you want to have something called right, which essentially does the opposite. It's shifting everything to the right by 1. And because you want to make sure you don't have a ones off error, you subtract by 1. Next, you basically make the mask into a complement. So I'm going to make it called mask 2 equals left or right. Then you're going to finally do the clear the bits stuff, which is the most difficult part. So we're going to have cleared equals to n, actually no, not n, sorry, k and mask 2. So this is the clear the bits part for the algorithm. Then you have shifted equals to, now Gale uses m, but I'm going to use instead j because we're trying to make it a little bit easier. J shifted by I. So this is going to move m to correct position. And then finally, of course, you return a choice of essentially the divide and conquer. So return either cleared or shifted. And there's your algorithm. So if this algorithm is making, no sense to you, I would highly suggest understanding the concept of bit shifting in terms of like divide and conquer. Otherwise, we can move on. So I saved my drawing just in case for future reference. And now I'm going to go on to the next problem set. So problem B, we got now Toph, who is, of course, the Earthbender that Avatar tends to enjoy. Like the Avatar team tends to have great benefit from. So Toph is given a set of rocks that she could Earthbend with. For each rock I in the set J, which is like a contiguous set J, Toph can Earthbend exactly one rock from a top rock to a bottom rock and vice versa, which means she could basically Earthbend both ways. Determine the shortest sequence of bottom rocks Toph can Earthbend, assuming that we have a maximum of 32 rocks in a row to bend, which means basically, outside of Avatar Last Airbender references, this means we cannot bend any more than 2 complements integer set of bits. So we're going to now, of course, give you a few moments to think about this problem and now tell you the solution. Great, so I'll tell you the solution now. Think of it almost like a guessing game for Toph. If she actually flips all the rocks, she can definitely, by brute force, essentially bend all the rocks, but that would just be too time-consuming and too energy-intensive for her. It's much better for her to simply just put the rocks like in an array structure and just sequentially, manipulate the rocks. So essentially what we have here is a bit of a flip to bit to win type of problem. But this is like almost the inverse of Gale's CTCI problem. So let me show you what I mean by that. So I put my whiteboard here, I put my problem here to be organized. And here we go. So here for the algorithm, you want to think about this for a second. Let's just do a quick drawing. Let's say, for example, Toph has rock I over here and rock J over here, and a bunch of rocks in between. So the most optimal case is that basically the shortest sequence of bottom rocks Toph can Earthbend, which is essentially ones, is that everything else is a bunch of zeros. Because the short sequence that she can basically turn this 1 into a 0 is just simply Earthbend the final rock. The worst case scenario for Toph is if everything else is ones and there's a lonely 0 over here, and because Toph cannot just, just jump around the rocks, like assume that these rocks are really hard to Earthbend, she cannot simply just jump around the rocks. She has to do them in sequence. That's like the worst case scenario. Then she basically has to mask everything else as zeros and then somehow turn the 0 to a 1. Definitely not ideal. Like it's like moving furniture with something in the middle. It's just not ideal for her energy-wise. So what's Toph going to do? She's going to use something called a flip bit, which is like indicator variable of determining whether she needs to bend or not bend the rock. So let me first save this. Let me clear my drawings and show you the general solution for the algorithm. So public int shortest bend. And you have n basically here. I'm not adding in type variables, this is just pseudocode. So if you cannot bend the rocks at all, if n equals to -1, you can basically return -1. You don't do anything in this situation. Otherwise, you can have a list of sequences. So list is going to be an array list of sequences. Next, you want to be able to determine the longest sequence. So you want to return longest sequence. And the longest sequence will just take basically list as a parameter variable. So that's method 1 for your solution. And because the solution is a little longer, I'm going to actually reduce the font a little bit here because it's a little bit big. Maybe not. We'll see. Next up, you got public, I guess, get alternating sequence. So this is where you determine whether Toph is to bend or not bend the rocks. So you get another array list of sequences called this list2 equals array list integer of sequences. And essentially here, you want to determine what type of rock can Toph really bend. So you want to have 2 variables, a search variable and a counter variable, both originally set to 0. Then basically for each rock to Earthbend, this is all pseudocode, so it's not really going to make any sense Java-wise. For each rock to Earthbend, Toph is going to do the following. If the nth rock and 1, which is like this flipping the bit, happens to be not equal to what she is looking for, which can happen, especially in the worst case, then she's going to do the following. She's going to add the non-bended rock to the sequence or to the list 2. And then she is going to essentially reset the counter. Otherwise, if she is able to bend the rock, she can do the following. Otherwise, here, she can essentially do the following. She can increase counter by 1. And then really shift twice to 1. Gale does 3 shifts. I think 2 is going to be enough. So here is your solution, at least partially. Before I continue, I do have to give one caution. This is all assuming the rocks are bendable, at least in terms of ordering. In the event that the rocks are randomly ordered, this algorithm will not work. So that's just a heads up to be careful with the algorithm. Cool. I know this is a bit messy, but this is what Zoom basically only allows for space for the algorithm. So I'm going to save this and then make the rest of the algorithm here. So the final method for this algorithm is going to be finding the longest sequence. So public int find, or in this case, find the shortest Earthbend. for the rocks. And they're going to take an array list of integers, or in this case, rocks, integers as the sequence. So this method is a little easier. There's not too much manipulation going on here. You want to basically determine the min sequence to be equal to 1. And then basically, again, for each alternating rock to earth bend, which means I plus equal 2. So for each alternating rock to earth bend, this is the type of question that could trip up some interview in terms of like understanding it. You want to have 3 variables this time. You want to have one variable that's essentially just the position one, or in this case, the zeros sequence. And you want to basically get the ith sequence number here. Moving on forwards, you want to also have another variable called the sequence prev. So in this case, it's like the previous alternating sequence. And once again, I'm going to use Gale's little ternary solution for this. And then, of course, you have sequence next. So it's almost like a cipher. This problem is quite difficult. It's going to take a little bit of time to understand. So if you have any questions, please ask in the comments or GitHub comments, or even on my website. This problem is generally at least a LeetCode medium for difficulty. So if you don't understand it at first, just read the CTCI solution, and then you'll understand. This one took me a while to figure out. So now essentially we get into a guessing game. So we have a flip bit indicator, like I mentioned before, in this case, flip rock bending, which is going to be set to 0. And then if the 0 sequence happens to be 1, you merge. Otherwise, else if the sequence is greater than 1, you don't quite merge. You instead just simply add a rock to bend on either side. And then finally, this is very important, else if the 0 sequence equals to 0, you do nothing, but you actually remove a rock to bend on either side. So far, this is really similar to what Gale's solution CDCI has, which you might be thinking, Jason, aren't you just plagiarizing Gale or something? That is a valid assumption. And if you ended the problem at that, you probably would accuse me of just copying off Gale. Here's where things get to be different in this particular problem set, is how you end the problem. Because this is a min return, you're going to have to do something called min sequence. So you do math.min, either the flip rock bend or the min sequence. And then, of course, you return min sequence to end the problem set. So this is a lot, as you can tell. If you have any questions, just comment or ask basically what's going on. So essentially, the takeaway is understand why we have the flip rock bending, why we need to have basically like a cipher of previous and next sequences, and essentially why do we need to even worry about the min? Because we're trying to find the shortest sequence of bottom rocks or 1-bit rocks that Toph can earth bend. So that's it for problem 2. So I'm going to go for problem 3 with the proof of contradiction, and problem 4 will be pretty straightforward. So that was actually the hardest problem of today's episode, problem 2. Normally, I put the hard ones on the bottom, but I decided to switch it up for Mother's Day. It is definitely a nice way to keep people engaged in the episode. So I'm going to clear this out. I'm going to have now the final part of the second to last part. So problem C, the fire type. So in this episode, in this part of the episode, you want to basically show essentially a powers of 2. So you must solve an old Fire Nation puzzle with the two dragons, one that firebends with blue flames and one that firebends with red flames. Within each n amount of firebends between the two dragons, there is a dance move I and a firebend move J. So the moves are not the same. For each of the two turns, the dragon that firebends with blue flames will switch turns with the dragon that firebends with red flames. So devise an algorithm that proves this tautology correct. For each of the dragon firebending with the blue flames, the other dragon firebending with the red flames will have danced once. Or in mathematical terms, prove the following: k and k minus 1 equal to 0 is a way to determine if firebend k less than or equal to n is a power 2. And I probably put in a bonus episode, we use log mathematics here. I'm not going to go over that today. So I'll give you a couple of minutes to think about how would you prove this by contradiction. And essentially by the proof, essentially have your algorithm. So when Gail had this problem in her book, it was essentially a debugging problem. I think the best way to learn how to debug bits is to prove that the current solution is correct. That way you can understand the nuts and bolts of what you're debugging. All right, time for me to start sharing the whiteboard. So in this case, you want to be very careful with the proof of contradiction. I remember from algorithms class, this was one of those early proofs that tend to give issues. So you want to prove that P is true. Then you want to assume P not true and say at least a contradiction. So in this case, P is k and k minus 1 equal to 0. So let's assume, for example, not P, which is like logical deduction, k and k minus 1 not equal to 0. So if it's not equal to 0, what does that mean? It means basically you cannot have no two dragons that are firebending are on the same exact move. So this means that no two dragons can firebend on the same exact move. And that also means, very importantly, and this is where the problem gets a little more difficult if you try to solve it straight up, is that there's a pattern you want to do. So essentially, we're trying to put an induction within a proof of contradiction. And then that will essentially give us the algorithm. So let's say, for example, the easiest case, there's only two moves that they can choose. So dragon 1 chooses one move, dragon 2 chooses another. If there's 3 moves, dragon 1 can choose one move, dragon 2 can choose another move, because this is alternating, it's in a circle essentially. It's like Zuko and Aang learning how to firebend. It's in a circle. You can do that. So what happens if you have n moves if you're using induction? You have dragon n minus 1 choosing one move, dragon n choosing another move, and once again, you have dragon n plus 1, but the same as n minus 1. But wait a minute, this problem says that the dragon is danced exactly once, but we just saw that the dragon danced exactly twice here. There's your contradiction. That means this solution is not right. So there's your contradiction right there. Because you just said that the dragon was able to firebend on the exact same move, but then you also said they've already danced once. It is a contradiction. So there's a contradiction saying that the firebending dragon with the red flame has already danced once before the firebending dragon with the blue flame. So therefore, by proof of contradiction, this thing basically essentially says it has to be a power 2 for each time for the dragon to be able to firebend. So let me just add some space here to show you the solution. So therefore, by proof of contradiction, we can tell that the dragons can only firebend alternatively on powers of 2. And that is your algorithm. You want to basically get each dragon to firebend on a power 2. So for example, you want one dragon to firebend on the first dance move. Then you have to wait until the second dance move, then the fourth dance move, then the 8th dance move to make sure the other firebending dragon have exactly danced once. And there's your solution. So we're now finally at the final problem of Algos in 10 Season 3, Episode 1. This is definitely a problem that I think requires a little more thought. So I'm only going to give you the most basic starting points. I can go back to this problem in a bonus episode. It basically comes down to pairwise swapping from KLC to CI. So I'll read the problem to you right now. So Aang remembers a final problem to solve in an almost pairwise swap problem between Airbender and his beloved Bison. Shout out to Appa. Fun fact, Appa is actually a palindrome. The problem is as follows. Given a particular air tempo A, we want to be able to pair with the fewest amount of swaps or instructions between I air nomads and J air bisons, given that each of the positions between the airbender nomad I and air bison J alternate between odd and even indices. So for example, Aang chooses Appa, somebody chooses somebody else, then I guess maybe, I don't know, like Tenzin chooses Appa's cousin. Like it doesn't allow you to choose the same bison twice. In other words, we need to implement a bit shifting mask algorithm to mask all the odd bits and mask all the even bits depending on whether the bison first chooses the air nomad or the air nomad chooses the bison. So this is like a mother and child reunion with the problem, essentially. And a great way to think about this is to think about this as almost like a pairwise swap problem, like a distance problem. So I'm going to quickly share my whiteboard again. So essentially what you have here is a distance problem. So let's say, for example, Aang is over here and Appa is over here. And Aang is located here in point I1, J1. And Appa is located in the point I2, J2. And the point can never be the same. So what is the naive case in this algorithm? So what's the naive case is you could basically have one instruction just directly going here. So you can have one instruction going here. And by the way, instruction is networking term for hop, essentially. It's like a computer instruction for a robot. But by Pythagorean theorem or by basic geometry, you can also have an instruction here, I3 go here. So you want to be careful with how you choose your instructions. You don't want Appa and Aang spending too long looking at other type of bisons. It's like finding partners. You don't want to spend too long finding other partners. You want to make sure that the bison and the air nomad are nice and happy with the least amount of switching around, because the air nation is all about balance, and switching around too much is going to cause balance issues. So the algorithm is as follows. The algorithm is as follows, basically. You want to have one method that allows you to essentially swap bison and avatar. And to take that, you only have one int end. And you want to have two variables here. You want to have either avatar chooses first, which means Aang chooses Appa first. And you want X and the hexadecimal 10101010, or in Gale's terms, bunch of A's. Otherwise, you have a bison chooses first. You want X or, and this one gets interesting, 0x 010101, or bunch of 5s. And here's what you want to return. You want to either return avatar chooses first, shifted right by 1 because you want to keep Aang moving in the line, or bison chooses first. And we'll keep on moving left shifting by 1. Now, this is Gale's general solution. However, there could be a case where Aang gets very lonely and there's no bison to choose. So if no bison left to choose, then Aang has to choose the remaining bison. Oh. No other bison left to choose. Like everybody else is taken, Aang just doesn't have a choice. Otherwise, life gets easier for him. He can start choosing the game. So there you go. That's just very quick and dirty solution for the pairwise swap. So yep, that's it. Happy Mother's Day. This is Jason Liu, season 3, Algos in 10, episode 1. If you want to do the problem all by yourself, or you want to review the solutions, I could share this website on my YouTube channel. And of course, the coding will be given later. So happy Mother's Day, and remember to keep your bits happy and merry.